The electric field 4 meters from a very long uniform line of charge is 840 newtons per coulomb. How much charge is contained in a 2.00 centimeter section of this line? So I have a long line like this, and I'm just going to imagine a cylinder that goes around that line like that. That cylinder is going to have a radius of 0.400 meters. Why am I going to use that radius? Because that's the only place I know the electric field. Okay. And then I want to know the charge enclosed. Well, the flux, the integral over the closed surface of E dot dA, is equal to the charge enclosed over epsilon naught. So I just need to find the charge equal to epsilon naught times the integral over the closed surface of E dot dA. So let's figure out that integral. That integral over the closed surface is the integral over 3 open surfaces: the left, the side, or cylindrical part, and the right. So this is the integral over the left of E dot dA plus the integral over the right of E dot dA plus the integral over the side of E dot dA. Now, we know the electric field points away from charges, which means my electric fields are pointing like this, straight away from the charge. So the electric field will be at a 90-degree angle to the area vector on either the right or the left side, which means these two sides will both be 0. Because we have chosen a cylinder, which is always the same distance away from the wire, the electric field over that entire surface is always constant. And because the electric field points straight out, and the area vector will also be straight out, this electric field and that area vector are always parallel to each other. So because they're parallel, I don't have to worry about the cosine of theta. So I just have the integral of E dA. And E is constant over the surface, so I can pop it out there. So that is just E times the integral of dA. But the integral of dA is simply the area of that surface. In this case, the side of the cylinder. All right, I can find that. So the flux is equal to E times the area of the side. That is 840 newtons per coulomb. Okay. Times 2 pi times the radius, 0.4 meters. That's the circumference around the cylinder, times the length, which is 0.02 meters. Remember, they said it was 2 centimeters. Area is pi, 2 pi r L. You might say, I thought the area was pi r squared. That's the area of the end caps The end caps have an area of pi r squared. But they don't really matter because the electric field was parallel to those surfaces, not normal to them. It wasn't parallel to the area vector. Okay. In this case, so 2 times pi times 0.4 times 0.02, that's 0.05 meters squared. Multiply it times 840, and that is 42.2. 42.2 newtons meter squared per coulomb. Then the charge enclosed will just be epsilon naught times the flux. 8.854 times 10 to the negative 12 coulomb squared over Newton meter squared. Multiply that times 42.2 Newton meter squared per coulomb. Notice the meter squareds cancel, 1 coulomb cancels, the newtons cancel. We're left with just coulombs. Multiply this times 8.854 E12 negative. Okay, and I get 3.74 times 10 to the negative 10, or 0.374 nanocoulombs. All right. Now you are going to work this problem. An infinitely long conductor has radius r, uniform surface charge density sigma. In terms of sigma and r, what is the charge per unit length? Lambda for the cylinder. And you're going to use that to figure out the electric field for radii bigger than capital R. Okay. So in other words, this is a long, thin conductor like this, and the surface area, or the surface charge density, is sigma. Okay. That is the charge per area. And knowing it's a cylinder, you need to find lambda, the charge per length. If you find the area in some form that's got some stuff times length, then this will be Q over stuff times length. You'll have the Q over L part, and you can put the length or the rest of it over there. Okay, and then you'll follow what I did to find the flux through a cylinder surrounding it with radius little r that's bigger than the radius of the cylinder. And you will use that to relate the electric field to the surface charge density and or the linear charge density. Something very similar is done in the textbook as well as in my other video lectures.